Good afternoon, everyone. This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending HetNets Up Close, Essential Steps to Successful Deployments, presented by Ixia and ThinkSmallCell.com. Our presenters today are David Chambers, founder and senior analyst at ThinkSmallCell.com, and Rahul Iyer, wireless product manager at Ixia. With that, at this time, I would like to hand it over to David.
Thanks very much, Kyle. My name's David Chambers. I'm the founder and senior analyst at ThinkSmallCell, and I've been looking at the femtocell and small cell market for quite some time. The agenda and structure of our webinar today will be that I'll present the first half of the session, looking at the market evolution of small cells, the terminology as it's evolved, and the densification of mobile networks into HetNets. I'll then hand over to Rahul, who'll talk about some of the technical challenges and explicitly look at examples of where testing and certain use cases are very appropriate. And after the conclusion, we'll have some question and answer session. So at any time during either my session, my talk, or Rahul's, do feel free to submit questions on the panel on the right-hand side of your screen. So perhaps the first thing to look at are the market drivers for HetNets. Now, I'm not going to take a huge amount of time because I think almost everybody on this webinar is familiar with the very large growth of mobile data traffic on mobile networks today. Whether you call it a spectrum crunch or a data capacity crunch is up to you, but certainly figures in excess of 50% compound annual growth rate for mobile data are not unusual. And that traffic is very visible both in the high urban, high density areas, the central business districts of our cities, as well as inside buildings where we're seeing the effects of poor in-building coverage being stretched by these high data traffic demands. So the question is really how to solve and address those market drivers. And I'd refer back to a 3GPP workshop held in 2012, where some of the best technical experts got together to study what was possible. And as you can see in the chart, they figured out that, of course, you can add some extra spectrum to increase capacity. But the issue there is that the same spectrum isn't available in many parts of the world. And so we've ended up for 4G with many different, I think it's over 50 different bands and variants for LTE. And that all adds a cost and complexity. You can, of course, add spectral efficiency. You can improve, just as we've gone from 2G to 3G, now to 4G. But we're close to reaching the limits of Shannon's law with LTE advanced. And there's very little more that can really be squeezed out of the system. So what they determined was that for those very high capacity requirements, really increasing the number of cells, whether you call them sectors or cell sites or small cells, is the only real way to get a substantial amount of capacity to meet demand. And so we come up with the term HetNets, and this is where you coordinate, often tightly coordinate, a large number of small cells with the existing overlay of macro cells, all sharing the same frequencies. And where you can tightly coordinate and control those, you get the best of both worlds, and you get very significant capacity increases. So if we then just move on and look at the different categories of small cells, there are really 4 different categories defined by the Small Cell Forum. The residential, very small, low-powered, simple units deployed already in millions inside many people's homes. And those were originally called femtocells and still are sometimes called residential small cells. The enterprise small cells, which are typically slightly higher RF power, which gives them a greater range, typically higher capacity, maybe 16 concurrent sessions. And those are deployed in non-residential buildings. And the definition here by the Small Cell Forum now is that an enterprise sector is any building that's non-residential, whether it's an office or could include public venues, conference centers, hospitals, even stadia. And then as we get into even more powerful, higher capacity small cells, we're looking at the outdoor urban densification. And sometimes those are called metro cells, picocells, also a term used. And those are more commonly, certainly there's more interest in 4G variants for those. And last but not least, small cells can be deployed in very remote rural areas where they provide connectivity in places that previously didn't have that, particularly enabled by low cost of satellite broadband that's become available. So I think it's quite important, as you see here, the four categories are all included in the scope of the small cell forum, but when you talk to some operators, they would exclude femtocells, and really when they're talking about small cells, they're looking at these three categories, and that can cause some confusion when you're talking to people, because the numbers don't add up if they're forecasting only one or other of those sectors. And another way of looking at that in the slide here is just to consider the difference between planned and unplanned deployments. So the first type we show is the residential femtocell. And the point of that is that the RF radio planning department typically wouldn't be involved and wouldn't see those until they pop up on the network. They're just not involved. When we then go on to enterprise small cells, again, they're not really that worried about what's happening inside the building and may not be that involved in it, but there may be some coordination between the entrance and egress points of a building. As we then move on to urban and rural small cells, those are very much planned, coordinated, prioritized by the radio planning department. They're very much targeting to be. And those initially were all 3G technology. If you look, there's a similar kind of thing happening in Wi-Fi, where again, residential Wi-Fi access points could be bought by you or me, plugged in almost anywhere. Enterprise Wi-Fi is perhaps a bit more designed and coordinated, where the property owner, the building owner, will think about where and how those are deployed and may well own or operate all of the Wi-Fi. And then again, there's a carrier Wi-Fi which is deployed very much in a controlled way by the mobile network operator, by the cable TV companies, and the fixed network operators today. As we see 4G being rolled out, actually the first type was the enterprise 4G small cells. Those have been deployed heavily in South Korea, really in building traffic, handled and managed very effectively and deliver high data rates. We've also seen some residential 4G small cells introduced, although that's still a very early stage of the market. And perhaps the most exciting type of small cell in the longer term are these 4G urban devices, which, as I said before, are something that's going to be carefully planned and executed. I think the next thing to look at is just how can you get more cells, or how can you densify the network? And I've identified 4 ways that I've listed here. The first one is just to take the existing technology that's deployed on the rooftops, the macro cells, and split the sectors. So this requires additional physical antenna to be deployed. You can expand from 1 to 3 or 6 or potentially even more sectors by deploying these additional antennas and installing some additional hardware on the site. But if you do that on those same sites, the trouble is that they may not be best positioned to make most use of that additional sectorization. And so the industry developed something called remote radio heads, which could be located nearby but slightly further away from the macro cells. And they would be connected usually through a very high-speed dedicated fiber link, or today it's possible to get microwave links that would allow the displacement of additional sectors in other places. And one example of that might be it's convenient to deploy an addition in a nearby shopping mall, just to provide some immediate relief from additional capacity. But again, those things are stopgap measures. And the third mode that we look to is the in-building systems, the distributed antenna systems, which take the existing macro cell signal, the RF signal, and pipe it around a building. In the past, that would have been done maybe with passive coax. Nowadays, more modern DAS systems can do that with fiber, or a combination of fiber and some Ethernet cable. And another advantage of DAS systems is that because they're operating at the RF level, they can share that system between operators. But typically, again, it's said that these systems need quite a bit of skilled RF design and engineering, and can be quite costly to deploy. I think that's something that the DAS industry is working hard to improve. And then the fourth method, of course, is that of adding small cells, which is really quite a different approach. Rather than a top-down, it's a bottom-up approach, taking a complete base station capability and designing it, shrinking it onto a chip. So there's a number of different chipsets you can buy, software available, which allows you to design a completely functional small cell, complete base station. And because it's got all of the processing, all the baseband processing located there, it allows, it only requires a relatively low speed IP connection back to the central network. Optionally, some of the larger deployments of small cells can have a local controller, some optimization of the signaling between the different cell sites. I think all four of those methods are likely to be found in networks in the not too distant future. Now, of the four categories, I'd really like to drill in quite quickly into two of them, probably where the most market interest is. Firstly, the enterprise small cells. Today, mostly 3G. There are a few LTE deployments. Perhaps that's because there's a strong focus on indoor 3G voice than data at the moment. But we are beginning to see models, and I can see in the not too distant future we'll have further announcements as multi-mode 3G, 4G and Wi-Fi capable devices are brought to market during this year. These are typically slightly higher RF power than maybe your residential units, and can certainly handle more calls. One of the important constraints is that if they can be powered by the same Ethernet cable that's bringing the signal to them, then it makes for something that's very, very easy to deploy and install. These, because they're 3G, are already compatible with pretty much all of the 3G smartphones deployed today, and so that ensures there's no additional cost or upgrade or compatibility issues. Now, there's some tens of operators have enterprise small cells live in their networks today, and some are certainly scaling beyond the tens of thousands of buildings. So the focus is less about technology now. The debate has moved on to the speed of deployment and the business model. How quickly can you install these things? Can you make use of the in-building wiring and VPNs or Ethernet cabling? Are there different business models where the enterprise themselves might contribute to the cost, or they could be outsourced or managed by others? And from my point of view, I expect this sector to be the largest revenue driver in the short term for small cells because they can be quickly deployed. There are fewer barriers, and the costs of operating such a small cell are lower. You don't have to pay typically for the site rental. You don't have to pay for the power. You may not have to pay for the backhaul. Looking at the different sizes of buildings that need solutions, if we could move on to the next slide. There are, of course, many businesses and many buildings that have a relatively small number of employees and could be perfectly satisfied by effectively a residential femtocell. And that's something that should be cheap and simple and easy to install. As you grow to maybe up to 50 employees, you're looking at something more like a 16-user standalone small cell. But again, you might only need one. It depends on the size of the building or the number of users are actively on calls. And again, as you grow into larger size buildings, you would deploy multiple 16-user small cells. And some designs are able to cope with a grid of small cells that can peer-to-peer communicate with each other and self-organize. As you get to that top end of that kind of size of buildings, and the line drawn is perhaps slightly vague, it depends on the situation, you might then want to introduce a local controller that can control a group of small cells, not just to optimize the signaling, but in some cases make it appear to the smartphones that there is only one or two cells and they're not handing over so much as you move around the building. And you also then move into the territory where a distributed antenna system may be more appropriate. So it's very much horses for courses as you look at these different sizes of buildings. The other type of small cell I'd just like to drill into is the urban small cell. Sometimes this was also called a metro cell, and the term picocells are also used here. The focus today really has shifted very much more across to LTE. And part of the reason for that is that these outdoor small cells are much closer to the macro cells. And rightly or wrongly, radio planners tend to be very concerned about how these two layers of the network will cooperate and coordinate between each other. When you're inside a building, you effectively, these days, are almost inside a Faraday cage, because some of the buildings with the latest construction materials don't allow the outdoor signal to penetrate quite so significantly. But when you're out in the street, you're very much more closely tied to the macro cell. And so when you're using 4G, there are a whole variety of different techniques that you can use to make sure that the different layers of the HetNet, the small cells and the macro cells, are coordinated and working well together. And I would say that generally there is a feeling in the industry that these 4G small cells will technically work and can provide the kind of higher capacity and throughput that's required. Kind of time frame for this will vary. I would argue that perhaps the more that networks which have less spectrum and more traffic would be needing to move into the small cell deployment earlier than others. But generally over the next 12 months, we can expect to see a ramp up of this technology. And so it's perhaps less technology question, and now that the discussion is moving across to site acquisition, the deployment process, what type of backhaul to be used. This sector, I think, overall is going to be the largest driver in the longer term for revenue, because it's not just the boxes that would be market sizing. It would be everything from the tools, the skill sets, the additional deployment teams required, and other capabilities. So it's quite important when this equipment is deployed that it's very quick and easy to deploy and requires low maintenance. It doesn't require additional site visits. Now, if you take these two things together, these enterprise and these urban sectors, you move on to a densification strategy, which at this stage with many operators is first of all making most of their existing sites. So we've seen them expand those sites to use all available spectrum. If they've got additional spectrum with 4G, then you'll light that up first. You'll add that LTE. You might well refarm some of the spectrum that you've previously been using on 2G or 3G and move that up to the more spectrally efficient 3G and LTE. But once you've done that, and possibly you might have expanded the sectors in your existing cell sites. Once you've done that, there isn't much more you can do. So you would first of all look for any in-building issues. Try and buildings which are soaking up a lot of the capacity and the resource in your network, in your nearby macro cells, and try and offload that by deploying in-building solutions. And then at the same time, you'd also be looking to densify the urban network, perhaps first by adding some microcells, some higher traffic devices in poor coverage areas, and also even smaller cells to match that traffic and usage demand. So it's very important that you know exactly where the traffic is, both indoor and outdoor, and that you can target carefully where you're going to deploy this additional capacity. And what that means is we've seen a wider ecosystem of skill sets, tools, capabilities coming into the small cell arena. So in the deployment side, aspects around site acquisition, installation, the project management, how quickly can you physically deploy these on the ground, and then various tools, the planning tools, self-organizing software that allows you to identify, target, and optimize exactly where and how these things are configured. In a moment, Rahul will be talking about some of the test and validation aspects, which are, again, very important to this, to make sure that as you radically redesign and change your network, you can de-risk it by testing and validating how it's going to work before you deploy it. And last but not least, we're seeing some commercial changes, some new business cases, outsourcing in ways that perhaps didn't happen in the past. Now, before I wrap up, I'll just share one of the small cell forecasts that we've seen recently. This comes from Joe Madden of Mobile Experts and isn't radically different to some of the other numbers we've seen. As you can see, the dark blue curve of residential femtocells grows incrementally. It's not something that's going away, but he's not predicting a hockey stick growth. Not for any technical reason, but simply he doesn't see a compelling business case for operators. Now, his classification, his split between enterprise and carrier deployed small cells is slightly different to what I've described, and that's why the light blue sector is slightly a smaller proportion, because enterprise would normally include some in-building cells that are deployed by carriers themselves. So as you can see, there is significant growth in both of those sectors. We're talking about a total of 10 or more million deployed per year, of which the enterprise and carrier are 5-6 million per year over the next, by 2018, which when you compare to the installed base of macro cells of something like 5 or 6 million is quite a significant and a radical change to the network structure. So in closing, I'd first of all like to point out really that small cells are now very much a mature and proven technology. Sure, there's new models, there's new configurations coming, but these things have been around and working live in networks for 5 or 6 years. And when deployed, they can deliver the capacity, the performance, when the traditional methods, the quick fixes and simple, obvious things have been exhausted. But in order to achieve that, we'll require quite a different deployment approach, more automation, simpler installation, and de-risking that deployment in different ways. So this is bringing a wider ecosystem into the small cell arena. And of course, one of the players doing that is Ixia. And I'd like to hand over now to Rahul to describe how that's going to work.
Thanks, David. That was quite insightful. Hello, everyone. So I'm going to be talking to you about the deployment strategies that will allow you to accelerate small cell rollouts. And to begin with, maybe we should follow up on David's forecast slide to look at the current market status, right? So the small cell market forecast is so far. But if you look at the current market status, a couple of trends become quite obvious. Firstly, most of the deployments are in the residential space. And carrier rollouts have not necessarily held up to the initial expectation, right? Now, this is not because carriers are not behind this concept. In fact, we know several Tier 1 carriers have announced major small cell deployment plans. So it's important for us to understand why there is a delay, right? There are various reasons for this delay. And in fact, in today's session, we're going to look at some of these reasons more closely and see how we could practically address them with more lab testing. Another trend that's actually catching on is small cells with multiple access technologies. David also mentioned this, but it's more like 3G, 4G, and Wi-Fi all coming together. And 4G becoming the predominant, and when I say 4G, I really mean LTE here, LTE becoming the predominant access technology this year onwards. Again, this is looking forward into rollouts that are to occur this year and onwards. And this is indicated by not just the carriers and research reports, but also the increased lab testing activities that we see around the world. Okay. So if we look at the main causes behind slow rollouts, it becomes quite obvious that these reasons actually fall in two key buckets. Okay, the first bucket is actually a logistical challenges that are logistical in nature. Things like zoning, getting permissions, right, which is going to be unique to each city, each county. And the hundreds of different use cases, right, that an operator has to take into consideration when they're about to roll out a network. We won't be digging into this category of causes. We won't be looking at this in today's session. Instead, we're going to be focusing more on the infrastructure-related challenges, the second bucket. And basically, we're going to look at how carriers could move faster towards deployments by testing and modeling these technologies in the lab. And when we look at infrastructure challenges, it's mainly associated with the unknowns. Okay, the unknowns around introducing new devices and technology to the network. And carriers are looking for a consistent model that they can scale across their network. Given that there are going to be so many different use cases, as in where there are so many different deployment scenarios for operators, for them to come up with this kind of model in a practical approach is is actually a critical need of the hour. And so basically, we're going to be looking at how you can test for mobility, interference, UV load, scale, test these new devices for these kind of challenges in the lab and arrive at a blueprint for deployment. This is going to be the focus for today's call. Before we proceed, I think it'll really help everyone if we look at topology. And it's going to be slightly different for an urban deployment versus an enterprise deployment. So let's look at what are some of the new devices that are coming into the network. So in an urban deployment, this is how a sample urban deployment would look like. Again, this is a very high-level view, but this does include some of the key devices that are coming into the network, which is small cells with 3G, 4G, and Wi-Fi capabilities, right, coming into the network, as well as these concentrator devices called Node B gateways, eNode B gateways. These eNode B gateways concentrate so many different small cells and represent them as if they are one to the core network. In an enterprise deployment, we're going to be seeing more of, again, small cells with some additional capabilities, like, for instance, a local gateway. Okay. Now, local gateway comes in for use cases like local IP access or selective IP offload, and this kind of functionality will be built into the access points, or if not, it'll probably be a separate device. But the concept is a virtual concept that can exist anywhere. And finally, in order to manage these new devices, we're going to be requiring some new technology, and that's going to be the SON aspect of it. There are two types of SON. SON that's distributed, which is again a virtual concept. A distributed SON is a SON algorithm existing in the eNode B, versus a centralized SON, where the SON algorithms reside in a central SON server in the OSS ecosystem. So these are some of the new elements that are coming in to a network, as well as new technology that's being rolled out. And often when a network evolves and it changes, challenges are actually associated with these changing aspects, right? So we're going to look into that further. And here we have the key changes identified as well as challenges identified. Let's go through them quickly. So with new devices, right, we have a bunch of small cells and gateways that are being introduced into the network. If we look at the small cells, it's predicted that there could be anywhere from 4 to 10 new small cells per macro cell. Okay, now that's an order of magnitude more, right, of the number of devices that the operator has to manage and control, orchestrate their network. And with the introduction of gateways, the topology is changing. Okay, so it's introducing some new use cases as well. So these are some of the challenges that the operators are facing when rolling out these new devices. Similarly, when you have small cells and a macro cell, there are at least 2 layers of access technologies, the macro layer and the small cell layer. And there will be interaction between these layers, right, around mobility. There could be interference-related challenges between the macro and the small cell. And this is of a major concern right now for operators that are deploying small cells. So they don't necessarily want to roll out small cells would interfere with their macro network and cause more problems than it actually solves. So this is an area of concern for operators. When we look at SON, SON is the way it is actually envisioned. It has phenomenal power. Okay, in the sense, it really is going to automate the operation of a network. Okay, so the SON use cases are around, how you can control the network more efficiently and automatically, so that operators can be more focused on rolling out new services rather than maintaining existing ones. Obviously, when you roll out a technology of this scale and scope, there's going to be concerns, okay? And this needs to be validated. It's a new technology as well, so it needs to be validated in a practical manner. So that's the challenge with SON. And finally, backhaul. Backhaul's always been a pain, if you ask operators, because in many cases, carriers don't own their own backhaul, and they have to find secure, expensive methods of backhaul for their access networks. And what they are really looking for with backhaul is, what is the minimum backhaul required for a certain quality of service? And the answer is not always, what the maximum that we can get, because that's going to be very expensive for carriers. So it's about optimizing it based on time, day, and so on. And there's a lot of planning data required for this. So with that, let's move into the test cases itself. So validating small cells, which is the first device that actually is getting, if you look at it from the access network perspective, this is the first device that the UEs are going to come in contact with. And it's really critical piece of the equation, right? That the small cells are able to deliver a certain level of quality of experience that the users are used to now. So you want to evaluate small cells for its functionality, but also test it under realistic network configuration. Network configuration that the operator network that's reflected in the operator's network, such as using the type of home eNodeB gateways that an operator would have in their network. And then, of course, test it against subscriber models that are very realistic in an operator's network as well. But this is basic functionality of a small cell, and this is something that everyone has to test and validate. And the way to test and validate that is, again, you could follow an end-to-end model wherein you're simulating just the UEs, and the rest of the network is under test. Or in order to have a more predictable result, maybe one way to test is to isolate the small cells and test them in full isolation. Another use case in the small cell, when you validate small cells, is LTE to Wi-Fi convergence. This is not a practical scenario today because the standards are still evolving. However, the technology will be there soon, and very soon operators will also have to validate an LTE to Wi-Fi convergence in the lab. Moving on, SON, right? I'm going to give a couple of examples for SON. This will probably give you an understanding of how to test SON. So in this, we're looking at SON as a distributed SON residing in the eNodeB. So when operators are going to be deploying small cells along with macro cells, invariably they are expecting interference. And one of the ways to mitigate interference is actually an algorithm called enhanced inter-cell interference coordination. I know it's a mouthful, but it's actually a very cool technology. It works where the eNodeBs talk with each other in real time. For instance, every 200 milliseconds, the eNodeBs would share information with each other around interference-related information. And they would use, both eNodeBs should use this information to avoid interference in the first place, right? So how do you test this? Of course, you can test this in the field but it's going to prove to be very expensive. If you don't test it, you'll pretty much be putting all your eggs in this basket where you don't necessarily know whether the results are going to be delivered or not, right? So in order to test this in lab, one way is to have a test tool that can actually simulate UEs, but also simulate neighbor small cells. And this would be a coordinated test where the neighbor small cell could indicate an interference pattern to the device under test, and the device under test would reflect on that interference data and adapt in real time, right? And the UEs could actually validate this information and confirm whether the EIC SON algorithms are working as expected. In a sense, trying to give you a measure of the compensation factor that the eNodeB uses to reduce interference. And of course, you can do this in reverse, where the UE simulator could simulate interference on the uplink, triggering the eNodeB or the device under test to manage interference with the neighbor cell. So when testing this in lab, you're able to actually keep all of these parameters under control, and you're able to test with more precision and predictability than while doing it in the field. Similarly, if you look at load balancing as an extension use case, load balancing is where you have eNodeBs in a neighborhood that exchange load information and balance UEs in a uniform manner. And the aim is very simple, right? To improve the quality of experience for the user, and secondly, not to increase unnecessary handovers. Okay, so these are two key requirements for load balancing. And the way this is done is, again, eNodeBs talk to each other in real time and configure the handover parameters so that UEs are handed over and balanced in a more uniform manner. And again, with the test system which can simulate the neighbor cell and the UEs in parallel, that is a test system that has U interface and an X2 interface, this kind of simulation is actually fairly straightforward. You could target use cases around validating corner cases as well as negative cases by programming this test system to react in specific ways. Okay, so we could load as an example, we could load the target cell. We could load the device under test, and the device under test would trigger the load balancing algorithms to adjust with the neighbor cell. eNodeB gateway, again, moving on to the next device that's being introduced. An eNodeB gateway is actually a concentrator that is a critical part of the network. If it's going to face a lot of load because it's going to concentrate a lot of eNodeBs in the region. And when you validate an eNodeB gateway, apart from the obvious load and performance related validation, you might also want to validate it for new functionality that is going to be introduced. Things like, for instance, LIPA and SIPTO functionality that would require the home eNodeB gateway in terms of functionality. And again, when validating the home eNodeB gateway, scale is an important factor. So if you use real UEs alone, that will not get you the scale, right? So the option is actually to use a simulator which can simulate eNodeBs and test the whole network in that manner, end to end. And this will allow you to scale to very large number of UEs, very large number of sessions, close to hundreds of thousands of eNodeBs and millions of subscribers. Okay, moving on, Wi-Fi offload gateway. Again, this is another concentrator device just like the eNodeB gateway. This needs to be tested for functionality like authentication and interoperability with existing cellular networks. as well as load and stress, load the number of Wi-Fi sessions to make sure that the Wi-Fi offload gateway performs under scale. Finally, backhaul testing. When it comes to backhaul testing, it's around working out what is the minimum backhaul required to deliver a certain quality of experience, right? And in order to answer this question, instead of relying on theoretical values, it's very simple to put together a test in the lab where you have UEs, UEs that are being simulated against real E-node Vs or small cells, which have a backhaul which is impaired. So this is an impaired backhaul right here. And this link can reflect things like a DSL link, a microwave link. It can have properties like packet loss, delay, and so on, which when you validate it in this form, it will give you the key parameters to what link is the minimum, what is the minimum requirement for delivering a certain quality of experience. So to summarize, HetNets are actually crucial to meeting the growing demand for wireless data services. And new technologies are really required to handle a large number of cells that will be deployed, right? And validating these devices and technologies is going to be challenging. And therefore, it actually requires a paradigm shift in testing. Realistic lab testing will allow operators to develop and validate their plans and arrive at blueprints that would scale to the requirements of complex network. Okay? It's a practical test strategy as well because it scales to the different deployment use cases. Otherwise, it's just it's not very practical to be able to field test the different deployment use cases that are out there. Ixia has actually published a book on this topic, and I would recommend it to anyone who's in this ecosystem. So I think with that, I'll conclude my end of the presentation. I want to thank you and open the floor for some questions.
Thank you, Rahul and David. This is Kyle again. We've had quite a few questions come in as you guys were talking. So actually, the first one, Rahul, is for you. In urban small cell deployment, which backhaul works better or easier, microwave or optic fiber?
I wish I could answer that question. I wouldn't know. An optic fiber is an obvious answer there, but when we say work, it actually is much more than just whether the technology works. It's about the cost aspect of it and whether the deployment makes sense. Again, there are several key inputs for this, which I don't have. And the one model that could be adopted is testing it in the lab with the test tools that we have to arrive at that data. And we could certainly help you in providing more guidance around that.
Okay, thanks. David, we have a question for you. How do operators prioritize where to add extra capacity?
Oh, that's a very good question, Kyle. It may seem very simple that you just look at where the greatest traffic hotspots are and deploy them there. But the factor that complicates it is that it's not just the total traffic. It's that much more resource intensive to deliver than others. So the percentage of the total macro cell capacity or cell capacity that's delivering a megabit to you may be considerably more than delivering a megabit to me, because you might be indoors and the signal might have to penetrate through difficult RF conditions and so require extra protection bits or lower modulation rates. So the calculation that needs to be done is to measure how much total resource might be released by deploying a small cell somewhere, for example, indoors, by lighting up a building that's got not just a lot of traffic, but again, resource intensive. You might free up a considerable percentage of the outdoor network for the use of faster moving traffic and that couldn't be served otherwise. So I think when operators are prioritizing, they are using, or they need to use, more sophisticated tools that can model that, take account of that, and secondly, add the cost of deployment as a factor. So again, the cost of an indoor site may or may not be cheaper than an outdoor one. And so taking those two critical factors into account is probably a more difficult calculation that has been in the past. And again, that's why we're seeing, more sophisticated planning, performance management tools taking that into account.
Okay, thanks, David. Another question we had come in, which kind of relates to that, and Rahul and David both feel free to comment on this, is currently, are you seeing more deployment indoors or outdoors?
So I think as I said in the presentation, the indoors have fewer barriers to deployment. Part of that is that the kind of products you require don't have to be as robust for indoor deployment. It's in typically a supervised location that's got a temperature range that's comfortable to human beings, so it doesn't have to be as weatherproof and rainproof. And it may well be done with the permission or even the encouragement of the building owner, who can provide power and backhaul. So the deployment indoors should be the faster and easier one to happen. But that's not to say that deployment outdoors isn't and won't happen as well.
So if I can add on to that, it also depends on which markets we are looking at. If we look at North America, for instance, the enterprise deployments are actually behind the urban deployments. The various tier 1 operators have started rolling out the outdoor deployments, and the enterprise has some key questions around the business model, but also more around fundamental questions like neutral host. So it is an evolving market. A lot of these questions will be answered this year. That's what I believe. And these are changing numbers anyway.
That answer. So, Rahul, we had another question come in for you. Why is LTE a key access technology for small cells?
This is a very good question. So I think LTE is becoming the predominant access technology because the take-up rates. If you look at Verizon or AT&T, both of them have today at least 45 to 50% of their subscriber base that have LTE-capable devices. And LTE, according to them, is the fastest growing technology compared to the 3G days, or even 2G days, or even 3G and 2G put together. So LTE take-up has been really phenomenal and fast, and therefore they're predicting that a lot of their subscriber base will be on LTE soon. For them to deploy a network which is future-focused, future-looking, makes sense, and that's why LTE is becoming, a key piece of the small cell, key access technology in small cells. And of course, Wi-Fi to complement it makes absolute sense.
Okay, thanks. David, we had another question come in for you. You didn't mention Cloud RAN as a densification method in your presentation. Isn't this valid too?
Yes, it is. I guess part of the reason for maybe not calling that out explicitly is that I would see it really as another form of the remote radio head configuration. It's just that the cables potentially could be much longer optical fiber. Again, with a Cloud RAN, you would have the radio head dotted around many places, connected by typically dark fiber all the way back to the a central point, which wouldn't just be one base station. It may well be a whole data center full of baseband or a shared baseband processing resource. Arguably, the advantage of that is that because you've got all of that in one location, you can coordinate the signals even more tightly and efficiently and squeeze some more efficiency out of the network. But the downside is you do need dark fiber to every single place, which in as many countries as we might like. And I think if I could just briefly answer one of the early questions that you asked, Rahul, would you use optical fiber or would you use wireless in urban small cell deployment? I think if we had access to low-cost, prevalent fiber in the urban environment, then yes, of course you'd use that. But the reality is that's not the case in many cities, and so it's thought that you would have probably fiber to a hub, whether it's a macro cell nearby or one of the small cells, and then from there you'd have relatively short range wireless links, typically up to a few hundred meters. And there's quite a competitive situation at the moment with a whole variety of different wireless technologies being touted for that very last few hundred meters connection.
Okay, we have time for just one last question.
Two answers for one. Back to you, Kyle.
Okay, we have time for one more question, and I'd like to get both of you guys to comment on it. Maybe start with David and then move on to Rahul. So where do you see, or how do you see small cells contributing to LTE advanced deployments in the future?
So LTE advanced isn't just one baseline. It's really a pick and mix in the sense that there are a variety of different features included in it. Some of them, like carrier aggregation, allow you to take multiple frequency bands, glue them together and get faster data rates. And that's something that's certainly going to be deployed widely. I would expect that to be deployed both in the macro cells and in small cells to achieve that. Others require extremely tight coordination, so that the phase timing and the signaling coordination is in fact so tight that you can't, the Metro Ethernet Forum are saying that they can't guarantee to get the messages between the eNode Bs within the kind of millisecond time frame that's required for this to work well. So they would only really be feasible in a Cloud RAN configuration. And that means, from my point of view, that they wouldn't be used in small cell, at least in the most aggressive form. Something like COMP is an example of that. And they would only be deployed in very specific, tightly engineered scenarios.
Yeah. So my opinion is very similar. I think LTE Advanced is key for the take-up of small cells. So specifically speaking, I think carrier aggregation and SON, a lot of the SON use cases like EIC are also release 10, which is LTE Advanced release, right? So it'll become table stakes. So today, small cells, one of the requirements for small cells is that it will have multiple radios like 3G, 4G, and Wi-Fi. There is a very obvious evolution path here, which is the 3G to be replaced with 4G. So you could have dual carrier in the same unit, and it's very much a table stakes game. And same thing with SON. With regards to some of the advanced technologies like coordinated multipoint that David was talking about, it makes sense in some deployments, and so it'll be a pick and traders may do it, others may give it a pass. EMBMS is another such similar technology, right? So things like this will be more ad hoc. The table stakes would be carrier aggregation, I think, and so on.
Okay, thanks. That's all the time we have today. I want to thank David Chambers, founder and senior analyst at ThinkSmallCell.com, and Rahul Iyer, wireless product manager at Ixia. Thank you, guys.
Thanks, Kyle.
Thank you.
And I also want to thank everyone for attending HetNets Up Close, Essential Steps to Successful Deployments, presented by Ixia and ThinkSmallCell.com. Thank you.